Here's Unit 1, Exponents Study Guide, Part 2. For number 11, you have to select all expressions that equal 7 to the 8th power. So let's look at choice A. Choice A would be the product of powers. The bases are the same and you're multiplying. Keep the base, add the exponents. So A does equal 7 to the 8th power. Let's keep looking because it said select all the expressions. So for letter B, we would multiply its power rule, power of a power. So it would be 1 to the 3rd over 7 to the 6th. This one does not equal 7 to the 8th power. For choice C, it's the power rule or power of a power. When we have an exponent raised to an exponent, we keep the base and multiply the exponents. A negative times a negative is a positive. So choice C is also one of the answers. For letter D, it's quotient of powers, where you keep the base and subtract the exponents. This would end up being 7 to the 4th power. So choice D is not an answer. And finally, choice E, in the numerator, we would keep the base and add the exponents. And then we'd have to keep the base and subtract the exponents. So choice E does not equal 7 to the 8th power. So only A and C for number 11. For number 12, we're going to simplify the expression. This is a multiplication problem, and we do have some like bases, so we could use the product of a power. So starting off, I noticed that there are coefficients, different bases, 9 and 2. That requires just straight up multiplication. So 9 times 2 is 18. Next, we have the like bases of B. For product of power, when the bases are the same and we're multiplying, we keep the base and we add the exponents. So 7 plus negative 2 equals 5. Finally, we have the like bases of C. C to the 6th and C. When there is no exponent, the invisible exponent is 1. So we keep the base and add the exponents. Our final answer then is 18, B5, C to the 7th. For number 13, we have a division problem, so we can use the quotient of a power. Quotient of a power says when the bases are the same and we're dividing, we keep the base and subtract the exponents. We also have coefficients in this problem, so we'll start off by doing regular division with those. 28 divided by 7 equals 4. Then we'll look at our p's. We keep the base and subtract the exponent, but be careful here. This is 2 minus 5, which equals a negative 3. And then we'd look at our q's. Keep the base, subtract the exponents, and we get negative 9. Now we should do one more step in simplifying. Because we have negative exponents, these should become positive fractions. To make them positive fractions, we need to put them in the denominator or make them into positive fractions by taking their reciprocal. So p to the 3rd and q to the 9th. We can leave the 4 in the numerator because 4 was the coefficient. Plot and label these numbers on the number line. To do this, I would evaluate each expression. So for the first one right here, 2 to the 2nd power, that equals 4 because it's 2 times 2. So on 4, I'm going to do 2 to the 2nd power because that falls exactly on 4. The next one, negative 2 to the 1st power, is negative 2 when I evaluate it. So negative 2 to the first power would fall right on negative 2. Negative 1 to the third power would still be negative 1 because it's negative 1 times negative 1 times negative 1. So that one would fall right here. One half to the second power, that's 1/2 times 1/2, which is 1/4. 1/4 would be about right here. So I would put that. And finally, anything to the 0 power equals 1. So 1/2 to the 0 power falls right on 1. Solve for x. So for x, we need to figure out what to the second power, or what times what, equals 81. If you didn't know offhand, you could take the square root of 81, which is 9. So x would equal 9, because 9 times 9 is 81. Number 16 says x to the third power. So what times what times what is 64. So I could do some guessing and checking, or you could do the cubed root of 64. Oops, I wrote 63 there. And the cubed root of 64 is 4. So x would equal 4, because 4 times 4 times 4 is 64. Solve and show all of your work for number 17. The Pyramids of Giza are a true wonder of the world. These pyramids were built between 2589 and 2504 BC in the desert just outside Cairo, Egypt. The Pyramids of Giza are one of the oldest examples of square pyramids. The base of a pyramid is a perfect square with an area of about 18,500 square meters. Use the space below to model the problem and show your work for answering each question. Now the key here is that the base of the pyramid is a square. So I'm going to do a little sketch of a pyramid, of a square pyramid. Not that great, but now I'm going to pull out the square, the base of the pyramid. So that's square, so I'm just going to try to draw close as I can a square base. The base of this is 18,500, the area of that base. So we're looking for each side length, because I looked ahead and it says what's the perimeter of the base. So to get one of the side lengths of a square, we would have to think, well, area is length times width, and each side would have to be the same. So because it's a perfect square, we could take the square root of 18,500 to get the side length. So remember, in our calculators, we would do second function x squared and then put in 18,500. So when I put that into the calculator, I get approximately 136. Now it does trail on. It's not a perfect square, so it's going to go on. For our purposes, I would round that to 136. Now, the perimeter is the distance around the square. So we would have to take 136 and add that 4 times, because there's 4 sides of a square. When I add all that together, I get my final answer of about 544 meters. as the perimeter. So the key here was it was a perfect square. And because it's a perfect square, I could take, and we knew the area, I could take the square root of that to get a side length, and then take that side length and add all around the square to get the perimeter.